Alright, welcome to Kinematic Equations Part 1 video. This is basically the definition of kinematics, all these things listed here. How an object moves, how far does it go, how fast does it go, how fast does it get faster, how fast does it get slower, how long does it take, and all the equations that go with it. Here's the symbols. You saw those in the last video.
It's just like what they see on that units quiz where they have to fill in the term or the word.
Yep.
And the symbol that goes with it. And, of course, those two pieces are on the cheat sheet of science that they get to use for their formula chart. And then lastly, they have the units.
You should know these by now. If you don't, learn them. Alright, solving problems using the guess method. These are just a couple reasons of why we use the guess method. Guess stands for given a known equation, solution solved. We'll discuss that in more detail here in a little bit. But it's a method of successful analysis of a word problem. Great way to show your work. Great way to organize the work that you show. And it's a way to be sure your solution is complete.
All right, so more on the details. The G stands for given. It's where we identify the given information. Of course, sometimes we have hidden information. If we say something starts from rest, that hidden piece of information is initial velocity would be 0 meters per second.
Also acceleration due to gravity. We're not going to give that to you, but if you don't know that by now either,
learn it.
Good luck.
The U stands for identifying the unknown, so we need to figure out what it is we're solving for. The E is figure out what equation are you going to use. Well, once we list the givens and the unknown, we're looking for the equation with all those letters in it. S is substitute, the other S is solve. Again, this is a fancy way of showing your work.
Also, that's those units quizzes that you get. Remember the givens, unknown, and equation that you're going to use.
You mean where they have to write the physics term and the symbol and the unit?
Say what?
And pick their equation.
Yeah.
Okay. So let's start off with an easy one. We're going to look at average speed. Average speed is the distance traveled divided by the time it took to happen. So another way to write it is change in distance over change in time. Delta means a change in. So that's what when they see the little triangles, we're talking about the change in something. So here's our first example. Jessie drives 6,000 meters to get to softball practice. The practice field is only 4,000 meters away from home if she could use her hovercraft and fly straight to practice. But since she can't fly, she has to make right and left turns along the way.
Yep.
So we want to find her average speed if the total time for the trip takes 500 seconds.
All right, so important things to note are speed. And why are we using this one instead of that one?
Well, 6,000 meters is her distance.
Okay.
4,000 meters would be the displacement. Speed is the distance
over
divided
time.
by time.
Okay. So, do I have an acceleration?
I don't see one.
Do I have a final velocity?
I don't see one.
But that is what I'm trying to find, technically.
Yes.
Velocity.
We're going to be looking for velocity.
And I don't care my initial velocity. Do I have a time?
Sure do. 500 seconds.
500 seconds. And my distance is?
6,000 meters.
6,000 meters. So, Ms. Crow, what equation am I going to use that has V, T, and D in it?
I'm going to use V equals D over T, which can be found on the cheat sheet of science.
Cheat sheet of science. So what am I looking for? I'm looking for V, so I keep V there. My distance is 6,000 meters, and my time is 500 seconds. So when I take 6,000 and I divide it by 500, if my BYU math serves me right, that would be 12 meters per second. So look here, I have meters over seconds. That equals my units for average speed, meters, 12 meters per second.
That's awesome, Mr. Ben.
Thank you.
All right, now let's calculate a velocity. Velocity is displacement over time. So now we're looking at the change in your position, where you started to where you ended in a straight line, which is different than distance. Distance includes all those right and left-hand turns.
I'll start drawing with that. All right, here we have the same question, but it looks like we're using the 4,000 this time.
Okay, so again, we've got Jessie driving 6,000 total meters to get to softball practice, but the practice field is only 4,000 meters away if she could use her hovercraft. So now we're going to, let her use a hovercraft. She's going to fly to practice. We're looking for her average velocity. Again, the trip takes 500 seconds. So Mr. Ben is identifying all the things that are given to us. We don't have an acceleration. We're looking for a velocity, and our displacement was 4,000 meters, and our time was 500 seconds. So he's picked an equation that has a v and a d and a t in it, of course, all with those vector arrows. So we're solving for velocity, his displacement over time. He's substituting 4,000 meters in for the displacement, 500 seconds.
So you for that.
For the time, my Oklahoma, OU, Boomer Sooner, math says the answer to that problem is 8 meters per second.
TCU, by the way. That's right, BYU lost to Utah State, so no big deal. What's the, I digress. What is the...
Got totally distracted there, Mr. Ben. 8 meters per second.
8. Taking opposite class, though. All right, so meters per second there, once again, is our unit right there, meters per second.
All righty. And I want them to notice that the speed was 12 meters per second, the velocity was 8 meters per second. They weren't actually the same answer.
Did you guys notice that?
Well, I hope they did. Now they're talking back to the computer screen right now. All right, so now let's calculate acceleration. So we're going to look at the change in velocity over time. So we've got a delta V, so that's the change in velocity over the delta T, the change in time. Another way to write that would be VF, for my final velocity, minus VI for my initial velocity, all divided by the time it takes for that change to happen.
All right, car starts to accelerate from rest. 3 seconds later, the car is going 20 meters per second. What is the car's acceleration? All right, so important things are that puppy right there, that thing right there, and that right there.
Well, what are all of those that's and this thing and that puppy?
All right, I am looking for the car's acceleration. That is what I'm looking for. That is my unknown.
Okay.
All right, my final velocity is how fast, or velocity is in meters per second, how fast it's going at the end of the problem, or the last velocity that we have.
You mean that subscript is an identifier that tells us that is the velocity you are going finally when you are all done?
Yes.
Okay.
Final. Now, initial is your first one, so what was my initial velocity?
That's that hidden piece of information. Rest,
From rest
means 0 meters per second.
0 meters per second. And the time was?
3 seconds.
3 seconds. So do I care about the distance?
Not right now.
All right, equation. Let's see. What equation do I have that has acceleration, final velocity, initial velocity, and time?
I know. It's on the cheat sheet of science.
The one that you just gave us.
A equals BF minus VI all over T. So now we've done the G, the givens. We've done the U, the unknown. We've picked the E, the equation. Now Mr. Ben is substituting and solving. 20 minus 0 all over 3 seconds. So 20 over 3 seconds, which gives us 6.7 meters per second squared.
Now, once again, I didn't put the units in, but I will right now. We have meters over seconds divided by seconds.
So when you keep all that,
that equals meters per second squared.
Awesome. Let's keep going. All right. Oh, Mr. Ben, I just got scared.
What?
There's like fractions and squared things.
All right, well, you'll use all of these, and you'll get used to using them. Here they all are. These are all on your sheet. We'll use these. We'll do these.
Wait, they're on the cheat sheet of science?
Yes, they are.
Okay, now I feel better.
Purple, salmon, whatever color your cheat sheet of science is in your class, and then what they all mean: initial velocity, final velocity, acceleration, time, and displacement. So let's use one of those on this equation here. I'm sick of reading readings for rich people. You guys do it.
A cyclist is riding down the road at 5 meters per second.
All right, what's that one?
Initial velocity.
Okay. 5 meters per second. Okay.
Okay, the cyclist begins pedaling faster when he's accelerating at a rate of 2 meters per second squared. That's my A. A equals 2 meters per second squared. He does this for 4 seconds. So that's my time, 4 seconds. What is the cyclist's velocity after this time of acceleration? Oh, so I'm looking for his VF. So D is unimportant at this moment. I'm looking for an equation that has VF, VI, a T, and an A in it. And sure enough, there it is. It's the same equation we used last time.
Now, I want to make a point here.
Yes.
That just because it doesn't say VF equals does not mean you can't use this equation. Because a lot of people are like, well, Mr. Ben last year, I was like, well, Mr. Ben, there's an equation that said VF equals.
True.
So just look for equations that have all of the variables in it. It doesn't have to be
you mean
that one.
Hang on. I want to draw now.
Yep.
You mean I'm looking for an equation that has all of these letters in it somewhere?
Yes, it does not have to be VF equals something.
Okay, so as long as VF is in there,
it's good to use.
I can plug in my numbers. I can do some rearranging. I'm set. Okay, so now we're plugging in 2 meters per second squared for my acceleration equals VF, that's the thing I don't know, minus 5 meters per second, that's my initial velocity, all divided by 4 seconds. Okay, great. I need to get rid of that 4 seconds, so I'm going to multiply both sides by 4. So I'm going to end up with 8 meters per second over on the left equals VF minus 5 meters per second. To get rid of the 5, I need to add 5 meters per second to both sides, and I end up with VF equals 13 meters per second. Hey, that's not so scary.
Sold.
Okay. All right, I'm going to keep reading, Mr. Ben. Is that okay with you?
Certainly.
All right, so we've got a track runner starting from rest. That means VI equals 0 meters per second. That's that hidden piece of information. The starter shoots the gun, and the runner takes off. The runner accelerates at a constant rate of 3 meters per second squared. Hey, there's my acceleration for 6 seconds. There's my time. Time equals 6 seconds. How far down the track has he run?
How far is the velocity, right?
No,
Heck no.
that is the distance. How far? And actually, if he's running on a straight track, the distance and the displacement would be the same in this case.
Really?
So when we go back and we look at that cheat sheet of science, we're looking for an equation that has a distance, an initial velocity, a time, and an acceleration. And Mr. Ben found that equation.
Yes, I did.
Change in distance
I did like that.
Equals VIT plus 1/2 AT squared. Keep in mind, only the T is squared once you start using this equation. So it's plugging things in. My zero was my initial velocity times 6, so that's my 0 times 6, plus 1/2 of 3 was my acceleration, and then 6 squared. So I've got 0, because 0 times 6 is 0,
yeah.
plus 1/2 of 3 times 6 squared. So that equals 54 once they plug it all into their calculator.
54.
So 6 squared would be 36 times 3, all divided by 2. That's going to give them that 54.
I can't quit adding them up right there.
Yeah.
0 plus 54, and it's in meters because it is a distance.
So there he goes, 54 meters down the track. All right, that's all we've got for this video. We're going to give you some more equation practice on the next one. Good luck.
Deuces.